My, Hi, my name is Mohammed. I'm going to talk about the ultrasound non-destructive testing. What non-destructive testing is when you use an ultrasound phaser to detect the voids in an object or in a material that is really expensive and you do not want to harm that material. And this ultrasound phaser uses a transducer that needs to be lubricated with an oil and against the material that we're using, so the sound waves can easily pass through the medium. That transducers check the distance of the material in the material that where the cracks or the holes are, so to display the to send them signals out on the screen, and it shows where what the distance is, or where the holes are on this material. And this ultrasound inspection is a non-destructive method in which beams of high-frequency sound waves are introduced into the material for the detection of substance flaws in the material. And the sound waves travels through the material, and when there's a loss of energy in there, they're reflected back from the at the cracks or the holes to show that there are the cracks or the holes in the material there. This is the where they are located. This is the way how the flaws are highlighted in the material. A usual UT inspection system consists of several functional units such as pulsar, transducer, and display devices. A pulsar is an electronic device that can produce high voltage electrical pulses. And driven by the pulsar, the transducer generates high frequency ultrasonic energy which goes through the material to show where the cracks are, and they're used with the highest sound energy, the high frequency. As a phaser uses a sound waves, and this sound energy was introduced and propagates through the materials in the form of waves, right? And that waves, when they pass through the cracks, when they hit a crack on the material, they reflect back, because the energy part of the energy of those waves will be reflected back, which shows that there are this place at this place the holes are located in this material, and those reflected wave signals is transformed into an electrical signal by the transducer and is displayed on a screen of the phaser, which shows in the different ways, like if the frequency is really high, and it shows on the screen everything. In the applet below, the reflected signal strength is displayed versus the time from signal generation to when an echo was received. Signal travel time with an directly related to the distance that the signal traveled.
Hi, my name is Noreen, and I'll be talking about the theory behind the ultrasound phasers. It has already described as to what it does, but now I'll talk in detail on how it works. The main idea here is it introduces high frequency sound waves into the material for detecting subsurface flaw. The second waves, they travel through the material and are reflected back when they hit the cracks. This way, the defects are shown and highlighted well. Now I'll talk about the functions of the UT inspection system. Typically consists of three things: the pulsar receiver, transducer, and lastly the display device. A pulsar receiver is an electronic device that can produce high voltage electrical pulses. The transducer generates high frequency as shown in this picture. Use and go through the material in forms of waves. When there is a crack or so in the wave path, a part of the energy will be reflected back from the flaw surface. So then the wave signal is transformed into electrical signal by the transducer and is shown on the screen. Again, this slide shows you how the probe generates sound waves into the material. The left picture shows the sound waves being reflected back without any cracks. The right picture shows defects which create a third indication and simultaneously reduce the amplitude of the back wall.
Hello, this is Vishdeep Singh. Phaser Access is an ultrasonic flaw detector utilizing a simple menu-driven interface. The Phaser Access offers all sections of industry a compact, portable, and effective phaser array UD solution. It has powerful 150-volt peak-to-peak square wave pulsar and is capable of using a wide variety of advanced phaser array probes. Transducer is a machine which converts one form of energy into another. Here you can see the basic user-friendly interface of Phaser XS with detailed components. To the very right is the function knob and the pulse connection. To the left is the screen and the buttons to operate the interface. These are all the operations associated with each button. Phasor access consists of a transducer, and to the end of this wire is the pulsar and receiver, which is placed over the specimen to be tested. This apparatus also has a probe that can test the flaws at an angle rather than a straight line if the path of the flaw is blocked. To start the experiment, subcoupling material is applied to the specimen. The main function of this coupling material is to remove any air bubbles that may come between pulsar and specimen, which can hinder the readings. After this, the pulsar receiver is moved over the surface of the specimen to be tested, slowly and steadily looking at the screen at the same time. The specimen here is divided into two parts. The upper half is half A and the lower is B. At the top of the interfaces screen, we can see the probability of the hole, which is shown by the slot saying P% B and P% A, which represents the half A, half B, respectively. Also, the distance from the top of the specimen is also provided in the next column, saying PDB and PDA, which means the distance from the top of the specimen to the flaw. Doing this, the distance is measured and recorded. The horizontal distance for the set of values is calculated manually with the help of the scale. By this, we can obtain the x and y values of the specimen containing the holes or the flaws and make a 3D sketch or find the coordinates for further usage. Thank you.
Hi, my name is Maz Rizvi, and in transient thermography, deep-seated defects in materials with low temperature conductivity are, is the purpose of thermography. Um, the material, the sample or the material is heated up over a long period of time in a furnace. Typically, delamination or a cavity is a thermal barrier for the heat flow. Now, when the preheated sample is brought in to normal climate, it starts to lose heat to the environment, and the defects are properly evident because of the inhomogeneous temperature, which is varying temperature, and it's a distribution on the surface, which is detected by the infrared cameras. Only one way from the defect to the surface of the sample is relevant for the measurement, which is heat. So the heat has to cover only half the distance compared to other thermal methods. This explains why it is possible to detect deep-seated defects in short time with this method. And now let's jump into laser stereography. So what this basically is a variation of holography specifically designed for NDT applications. So stereography provides full field, non-contact, non-destructive testing for samples. Stereography is used to highlight internal defects by locating strain concentrations after appropriately applying stress. Next one we're going to talk about is optical holography. This imaging method records the amplitude and phase of light reflected from an object as an interferometric pattern on a film. This reconstructs a full 3D image of the object. So the sample or the test sample is compared in two different stress states, which is mechanical, thermal, vibrational, it can be sound. Um, the resulting interference patterns, um, contours, the deformation undergone by the specimen in between the two recordings. So the surface, as well as as substance defects, show distortions in the otherwise uniform pattern. Um, this also reveals defects, thus making optical holography an appropriate way to locate defects. Thank you for listening.
Hi, my name is Steve Summerfield, and I'm going to talk to you about a few other methods of NDT. Magnetic particle inspection, MPI, also sometimes called magnetic test, MT, is a non-destructive test method for detection of surface and subsurface flaws in various materials. The test method involves application of magnetic field externally or applying electric current through the material, which in turn produces magnetic flux in the material. Simultaneously, visible Furris particles are applied to the test surface. The presence of a surface or near surface flaw in the material causes distortion in the magnetic flux, which in turn causes leakage of the magnetic field at its flaw. The magnetic particles are then attracted to that surface field, and you can see in our diagram how the flaw is actually detected by the shape that's created by the magnetic particles. Acoustic emissions testing, AE or AET, is a non-destructive testing method that's used to analyze emitted sound waves caused by rapid release energy due to defects in flaws. These acoustic waves are introduced by small deformations, corrosion, or cracking, which can occur prior to structure failure. AET is a method which evaluates the elasticity of waves caused by defects formed within the specimen. AET is often used to monitor such items like pipelines, bridges, cables. It can also be continuously used in monitoring structures such as mines. Radiography, RT, is also known as XT, X-ray testing, SRT, source radiography, radiologic testing, gamma radiography, and neutron radiography testing. All these are part of the radiographic family and are dangerous, expensive, and popular. The ability to be able to see inside things to provide a permanent historical image is made of one of the most popular NDT inspection methods. Radiography testing is the use of X-rays or nuclear radiation or both to detect defects in materials and to present the images in recorded media. Penetrating radiation is passed through a solid object onto a photographic film, resulting in an image of object's internal structure being deposited on the film. The amount of energy absorbed by the object depends on its thickness and density. Energy not absorbed by the object will cause exposure of the radiographic film. These areas will be dark when the film is developed. Areas of the film exposed to less energy remain lighter. Therefore, areas of the object where the thickness has been changed by defects such as a crack will appear as dark outlines on the film. Some common uses are detection in surfaces such as welded parts, casting, forgings, wall thickness measurement, corrosion mapping, detection of blockages inside of sealed equipment, detection of reinforcing materials in concrete slabs, and measuring bulk density of materials. And that concludes Group Alpha's video lab on ultrasound non-destructive testing as well as other NDT testings. Thank you. Bye.